as nothing is changing in time. And so right now we're talking about things that change in time. All right, so it's okay. So far we've discussed Maxwell's equations as being this: you get the divergence of E is equal to rho dot of epsilon naught. The divergence of B is equal to 0. The curl of E is equal to minus dB dt, and the curl of B is equal to mu naught epsilon naught. And it says using Stokes' theorem on Faraday's law gives us gives which idea. All right, so everybody is stuck on has chosen C or D. I think the correct answer is C, because that is that's Faraday's law, is the EMF produced by the Curly electric field. Here, let me annotate this a little bit better. Okay, so I think the answer is this one, right? Because what we're doing with Faraday's law is we're calculating a voltage, and the closed line integral around a loop, and if you do the electric field of that, that gives you a voltage, and that's equal to the rate of change of the magnetic flux. So we've dealt with, so we've taken the divergence of curls before, and if I take the divergence of the curl of B, what should that be? I'm not going to ask a poll. Let's just talk about this. Okay. So what is the curl of B? The curl of B is that. Right? So this would be the divergence of J. Do you guys remember what the divergence of J is?
0.
Not always. And the path in magnetostatics, it is 0. I agree with that. But it should be equal to the rate of change of the charge. So if we're let me put it this way, if we have a non-constant current density, then it's not 0. If our current density is constant, which we've always done in magnetostatics, it is 0. But it's not always 0. And so the idea is Maxwell's equations have to handle an event when J is not 0. And one of those events deals with this question. Okay. So in order to handle, in order to change Ampere's law, Maxwell added an extra term. Okay. He added this term because of this particular case you see here of a capacitor, right? And we're trying to find out the area in which we can integrate the rate of change of the curl of the magnetic field, right? So we had talked about when we do these area integrals, right, over where we have this one surface, the area is independent that we integrate across. You guys remember that? I think we did a few things about that when we were calculating fluxes. we had all these different shapes. When we were calculating electric fluxes, we used these different shapes. So what Maxwell realized is, in this capacitor situation, there's no current going across the capacitor, right? But this integral has to be the same no matter if I use this hash green area or if I just use the area that encloses this by this circle, right? They have to give us the same answer. So what Maxwell realized is the electric field between this capacitor can change in time, and I can use that to be similar as current, or I should say, this is usually called the displacement current. So in this question, it says the capacitor is charging, and we're going to ignore the edge effect. So I don't care about the electric field that's outside the capacitor. I just care about the inside. And they're asking for what's the rate of change of what is this integral of the curl of B. Well, there's no J because there's no current. So what we have to look at is how the magnetic field is changing, the electric field is changing in time. And the way Maxwell did that is he included it over the he extended the area that we're calculated over the green hatch and came up with the value we should have. It's mu naught I. So if we think about that here in a bit, let's say now the capacitor is charged. The capacitor is charging, but now I integrate over the traditional area where you think about if I have this loop, right? I just to worry about this area of a circle. What should the integral be? Well, the integral is not showing up. There we go. What should that integral equal to? Okay, I'm running out of time, so I'm going to end the poll. Share results. The answer should be B, because remember, when you do these area integrals, the answer is independent of the area you integrate across. It's got to be the same answer as long as the area is bounded by the same boundary. If I go back and look at the other problem, okay, it's the same boundary, it's the same loop inside, it's just a different area we're looking at. So we should get the same value we had before. Should be equal to mu naught I. So the ideal is Maxwell added a change to Ampere's law, and then we call these four equations Maxwell's equations. You know, for all, and these are valid for all electric fields and magnetic fields in space and time. So if, sorry, I hit the wrong button. There we go. So if we're in a vacuum, okay, so if we're in a vacuum, what's going to happen? Well, if we're in a vacuum, if I take the curl of E, I should get this. And then I can make a substitution for what the divergence, or I should say, I could make a substitution that the the curl of E is negative dB dt. Switch my operations of differentiation around. Then since it's in a vacuum, and if I plug that in there, I should get out a wave equation. And this is how Maxwell proved that electromagnetic waves existed. So you can do the same for B, and you get your answer. You get is you can get a plane wave answer that this representation. Okay, so I'm out of time. I'm going to stop right there. I just want I want to make sure that you understand that electromagnetic waves. This is how we prove that we get electromagnetic waves is using this strategy, and that in order to be a valid electric and magnetic fields, these equations have to be true. That's it. Now I'm done.